Hello everyone, thanks for coming. Today we are going to do a review of our week 10th lecture for the ODE course. In this week, we introduce the concept of ODE systems. Basically, the ODE system describes an interrelated variables x1 to xn. Each xi satisfies an ODE, but the right-hand side fi, they depend not only on xi but also all the other variables from x1 to xn. So if we can have n functions phi1 to phi n such that each of those phi I they satisfy this the corresponding ODE, then we call those phi1 to phi n to be one set of solutions to the ODE system. Specifically, if we specify the initial conditions and we wish to find a solution that satisfies the initial condition, then this system forms the initial value problem. Similar to the first order ODEs for one variable, we also have the existence and uniqueness results. If the right-hand side for those ODEs, their partial derivatives with respect to each xj, they are continuous in a region, then given the initial condition that falls in this region, there exists an interval such that the solution on this interval exists and is unique. A very special case is a linear system. For a linear system, the right-hand side is a linear function on x. If each pi they are continuous, then the system has a unique solution. If for all those gi they are 0, then the system is called to be homogeneous. Otherwise, it's called to be non-homogeneous. If both pij and gi they are continuous, then it has a unique solution. So before we start talking about ODE systems, we need to first review linear systems of equations. So if we have this matrix vector equation x equals to b, how can we solve it? First, if b equals to 0, then the trivial solution is x equals to 0. The non-homogeneous one is the case when b does not equal to 0. If the determinant of the matrix A is not 0, then we can write the solution as x equals to A inverse b. If the determinant of A equals to 0, then for the homogeneous equation, it has infinitely many solutions. For the non-homogeneous equation, the solution exists if the inner product of b and y equals to 0 for all y satisfying A transpose y equals to 0. So that is to say, the projection of b on the kernel space of A should be 0. The general solution of the non-homogeneous equation is x equals to a particular solution plus a solution to the homogeneous system. So for Ax equals to b, we can use the row reduction and the augmented matrix to solve the equation by hand. For ODE systems, we first need to clarify some concepts like linear dependence and independence for the solutions. So for k vectors, they are dependent if there exists non-trivial coefficient Cj for j goes to from 1 to k such that the linear combination equals to 0. For n vectors in Rn, if we let capital X to be the matrix whose columns are x1 to xn respectively, then the determinant of x is non-zero, is equivalent to linear independence of those n vectors. So for vector functions, linear dependence on an interval requires constants Cj that are not all 0, independent of t. So that is to say, the summation of Cj times xj equals to 0 for all t, and those Cj, they cannot be 0 for all j. We also talked about eigenvalues and eigenvectors for a matrix. Eigenvalue is a number lambda such that ax equals to lambda x for non-trivial, non-zero x. So the eigenvalue lambda satisfies the determinant of a minus lambda equals to 0. So the eigenvector x is the eigenvector that corresponds to the eigenvalue lambda. The eigenvalue they can differ by scalar multiplication. Therefore, they can also be normalized to have 2 norm 1. If for one eigenvalue, the algebraic multiplicity, which means it is the nth repeated roots of the determinant of the equation determinant a minus lambda equals to 0, then the algebraic multiplicity is n. It also has a geometric multiplicity, which means the number of linearly independent eigenvectors corresponds to the eigenvalue. The geometric multiplicity is always not larger than the algebraic multiplicity. Eigenvectors corresponding to distinct eigenvalues, they are linearly dependent. For Hermitian matrix, which means A equals to the conjugate of A transpose, they always have real eigenvalues, and their eigenvectors are orthogonal to each other. If it is a n by n matrix, then it always has n linearly independent eigenvectors. So for homogeneous first-order linear equations, it reads in this form: x prime equals to ptx. Specifically, if p is a constant matrix, then we have x prime equals to p of x. A set, any set of n linearly independent solutions of this system constitutes a fundamental set of solutions. If pt is continuous, then the fundamental set always exists from the existence and uniqueness theorem. In every solution to the homogeneous system, linear system can be represented as a linear combination of any fundamental set of solutions. Thanks for listening.